Mol ratios are the key to solving stoichiometric problems. Mol ratios come from the balanced chemical equation. You must have a balanced chemical equation before you solve any stoichiometry problem. So whenever you're given a chemical equation and you're doing a stoichiometry problem, check it. So let's look at this chemical equation here. It represents the combustion of a hydrocarbon, which we know always forms carbon dioxide and water as long as we have enough oxygen. I look on my reactant side, I see I have 5 carbons. On my product side, I only have 1. At this point, I know I have an unbalanced chemical equation. So stop this video for a minute and balance this chemical equation, and when you get it balanced, you can start again. So hopefully these are the coefficients that you came up with. 1 mole of pentane reacts with 8 moles of oxygen to form 5 moles of carbon dioxide and 6 moles of water. Notice I haven't included the phases here. It's not that they're unimportant, but I'm just going to really be focusing on the coefficients, so I'm not going to include the phases here. Alright, so now that we have a balanced chemical equation, we can move on to what mole ratios are. Mole ratios are derived from the coefficients in the balanced chemical equation. Now remember, a ratio is a comparison of 2 values. And there are lots of ways you can write ratios. The way that we're going to be writing a ratio is in this fraction format. So here are some examples of mole ratios. For these 3 mole ratios, I just chose arbitrarily to have oxygen in my numerator. So 8 moles of oxygen. Where did that come from? The balanced chemical equation. 8 moles of oxygen will react with 1 mole of pentane. Where did that come from? The balanced chemical equation. So what I'm doing is I'm comparing 2 chemicals to one another. The coefficients come from the balanced chemical equation. Mole is not written in the chemical equation, but we know that those coefficients can represent moles. And then the chemical formula is coming from the balanced chemical equation. 8 moles of oxygen, if it reacts with 1 mole of pentane, will form 5 moles of carbon dioxide. So here we have the ratio between moles of oxygen and moles of carbon dioxide for this chemical equation. And then lastly, we look at the relationship between oxygen and water. So according to this balanced chemical equation, 8 moles of oxygen, the reaction of 8 moles of oxygen will cause 6 moles of water to form. We're always just looking at 2 chemicals in a mole ratio. These numbers that I have highlighted here come from the balanced chemical equation, and we always have the word mole in there, as well as the chemical formula. Here's an example of some more mole ratios. Here I have carbon dioxide in the numerator. So 5 moles of carbon dioxide will form when 1 mole of pentane reacts. 5 moles of carbon dioxide will form when 8 moles of oxygen react. And 5 moles of carbon dioxide are formed when 6 moles of water are formed. So, mole ratios, always, always, always used in stoichiometry. If you are solving a stoichiometric problem, you will always use a mole ratio. Now, you may have noticed that there are lots of possible mole ratios to use. How do you know which one to use? Well, in a given problem, the given chemical, the chemical that you're given information about, is always, always, always in the denominator. And the desired chemical that you're trying to get information about is always in the numerator. So as I already pointed out, in a mole ratio, each chemical has a label of moles and the coefficient from the balanced chemical equation, and each chemical is represented by its chemical formula. So what is stoichiometry? Well, we'll be going through some examples pretty shortly, but in stoichiometry problems, you will always be given an amount of some chemical which you can find in the balanced chemical equation. And this amount may either be in moles or in grams. And in stoichiometry problems, you will always be solving for an amount of some chemical which is different than the chemical that you were given, but is also found in the chemical equation. So the conversion factor from the given chemical to the chemical you're solving for, which is different, is always, always, always the mole ratio. So super important that you know what a mole ratio is, and super important that you know where you get it from, the balanced chemical equation. And super important that the given chemical is always in the numerator, Scratch that. The given chemical is always in the denominator, and the chemical that you want is always in the numerator.